theorem in this video is going to be theorem 0.039. So theorem 0.039, I'm just going to say that if the diagonals of a quadrilateral, so quadrilateral bisect each other, which bisect means cut in half. So bisect each other, then the opposite sides of the quadrilateral are congruent. Just going to try to squeeze that in there. I don't think I can though. Are congruent. Alright, so let's go over the actual proof portion of this. So, proof. Given a quadrilateral, as we need to start out with that, quadrilateral ABCD. So let's just start drawing this. I'll draw it in orange. So let's label this one A, and we'll just go around in a circle. A, B, C, D. So I have a quadrilateral A, B, C, D. Let's see. If the opposite sides, if the diagonals of a quadrilateral bisect each other, so the diagonals have to bisect each other. So let's draw this diagonal and draw this diagonal. So this line's bisected, so these that means cut in half, so each side of here is equal. And then this line's also bisected by this other line, so we'll draw those marks to show those sides are equal. And we have to prove the opposite side, or that the opposite sides of the quadrilateral are congruent. So we'll say, let's say AC intersects BD at their midpoints. Could be a little bit more descriptive there, but the picture shows what's going on where they're both bisected at the midpoint. It would actually be, or never mind, we could draw a picture where only one's bisected at the midpoint, but we aren't going to do that. We'll say by the vertical angle theorem, angle, let's see, I want to get this angle right here. I need to label the center something. We'll label that point E. Okay, so we want that side angle. So this will be AEB. So angle AEB is congruent to angle, see, we want to get this side angle because it's the opposite one, so angle DEC. Then by side angle side, let's see, what can we say by side angle side? Oh, triangle AEB is congruent to triangle CED. So what do we have now? So AEB, because we have this side. A to E is the same as C to E, which is one line. And then E to B is the same thing as E to D, because they're both the two lines. So that's, and we know these center ones are, these are congruent. So we have side angle side. So finally, by corresponding parts, of congruent triangles, AB is congruent to CD. So AB is congruent to that. And notice we had to choose since we chose the first and last letter here, we had to choose the first and last letter here in the same order. Although we can then say after this that's congruent to DC or congruent to BA, but we don't need to do that. So let's see what we've proved. We need to prove that the opposite sides of the quadrilateral are congruent. Well, we've proven that, let's see, these two are congruent, and then we would, well, actually, yeah, I think I'll finish this proof. We'll do pretty much the same thing to show that these right here are congruent. So let's see if we can cheat this at all. We'll say, let's finish it in green. So, by, let's see, vertical angle theorem. By vertical angle theorem, angle BEC is congruent to angle AED. So we'll have these two congruent. So we have that side angle side. We can get side angle side for these two again. So then, by side angle side, triangle, let's say BEC, triangle BEC is congruent to triangle DEA. Let's see, what we're trying to prove again, the opposite sides of the quadrilateral are congruent. Okay, so we're almost done. Then, by corresponding parts of congruent triangles, parts of congruent triangles, let's see, angle BC, we'll say BC is congruent to DA. And we're done. Now let's just draw a little bit here. I'll do a hash mark in green. This one hash mark in green is not necessarily the same as one hash mark in orange. I just didn't feel like drawing out four of them or creating some other kind of symbol, so that's the way we're going to do it.